Hi everyone, welcome to Linear Model with me, Sarini Abdullah. For this session, we will still be doing model diagnostic checking and particularly for detecting homoscedasticity, that is the assumption of constant variance for the errors. So in the previous video, we already learned the motivation of doing diagnostic checking through residual analysis. And we also have learned about detecting lack of fit of the model. For this one, we will do detecting homoscedasticity. What is meant by homoscedasticity? That is the assumption that the variance of errors are constant, whether for small or big values of the the predicted values of the response variable. So what do we expect from the homoscedasticity? Of course, that because it is related to the variance. So in here we do the again, visually, we plot the residuals with respect to the fitted value or the y cap. So this is our y cap. This is our residual. That is the E in here. So then the variance of the residual, what we have when we say that the variance of residual is constant variance, it means that we want it to be, equally distributed, or if they are fluctuating, then it's okay, but the fluctuations should be like on the same pattern in the sense that we don't expect to have just small residuals over here and big residuals over here and then small again, something like that. We don't want it. We want it to be, like equally scattered all over the place around zero. And then there is no pattern, there is no certain interval where there is more variation of the residuals and a certain interval where there is like a big variation of the residuals. We don't want to have something like that. So shortly, we just want it to be scattered randomly, no pattern around zero. Again, with the limitation that, for example, like 95% of them are between the plus minus 2 standard deviation of the error. So this pattern is okay for us because it looks like there's no pattern in the variation of the residuals. While the one that we have in here, this one is not okay for us. It shows there is a heteroscedasticity, which means that the variance of the residual is not constant. Why this one indicates the non-constants of the variance, because we can see that for small values of the fitted y or the y cap here, for small value we have, okay, the residuals are relatively small, but then it's getting bigger and bigger and bigger and bigger and bigger. So in here, we can see there is a trend. So for this kind of pattern, if we have this kind of pattern in our plots of residual and the fitted regression, then there's a strong indication that the homoscedasticity assumption is violated in our model, and we really need to do something for that. So here is some examples of pattern in the that might exist when we plot the residual and the predicted values. If we have this pattern, then we can see that the variance of the residual is small, where for small value of y cap, and then getting larger and larger and larger as the value of y cap is increasing. So we can see that here the variance goes along with, the mean value of the the response variable y. So in this case, this happens for the data that follows Poisson distribution. And then for that one, we need to do some kind of transformation to make it, like equally scattered within the plus minus 2 standard deviation of that residual. Next one is that we might get this pattern that we can see, okay, the value is from 0 to 1, and then when the value close to 0 or close to 1, then the variation is just small relatively to when the value is getting closer to the center or to the middle of the interval. The data are more, varied in here, so we can say that the variance is getting higher and higher when the value close to half, and then the variance is getting smaller when the value goes to 0 or goes to 1. Of course, there's a clear pattern in here, and then we can think like that, okay, between 0 and 1, and then there's half. Probably this is kind of like the case when we have a binomial data, that is why it's just a binary variable. And this is also the other pattern that usually exists when we have the linear model. So in here, quite similar with the one that we have in here on the first one. So the value of the residual is getting higher and higher and higher when the value of y is increasing. But it's the difference with the first one is that it's kind of like, the increment in here is kind of like, kind of like multiplicative. So we might suspect that instead of having an additive model for this kind of result, we should propose a multiplicative model. So the one that I've explained before, if we have that kind of pattern, then we need to do some kind of transformation to have or to make the variance to be a constant, not having pattern. And that's called the variance stabilizing transformation. That is one way of approach to handle the problem of heteroscedasticity. And because here the variance that we are looking for is the variance of the errors or the variance of the response variable, they are the same. Then the transformation should be done to the response variable instead of the predictor variable. I mean that if you look at the previous videos, when we are detecting lack of fit, usually we do the transformation for the predictor variables, but in here, for the variance stabilizing transformation, it is needed for the response variable. Like what we've seen before, this kind of pattern usually happens when the data, when y follows a Poisson distribution, and if we can see kind of like, okay, a little bit more, kind of like curvature here. So it just makes sense, I mean that it's just intuitively reasonable to make it kind of like even, like this, okay? So we want to cancel out the effect of the curvature. And how to cancel it out? Then we have the square root transformation. So instead of having the model that is expected y equals or y equals x beta plus error, now we will propose the model square root of y equals x beta plus error if we have this kind of pattern in the residual plot. While for this one, like we've said before, 0, 1, and getting more variant as they goes to the middle of the interval. So it seems like this is a binomial proportion. So in this case, we should have the transformation that is the arc-sine square root of the response transformation. And the third one here we see before that this is kind of like a multiplicative model, and then again we want to here, like this one we want to flatten it, so it should be like have something like this, okay? And then to do that we can do the logarithm transformation. So So instead of having the model like this one, then we will have something like the logarithm of y equals x beta plus the error. To sum up, we can say that residual plots with no patterns, again, randomly scattered between plus minus 2 standard deviation, it shows a good fit of the model. And then we also have variance stabilizing transformation could be one of the approaches to handle the heteroscedasticity problem.